Today, we're diving into a fascinating story about data that seems a little too good to be true and what science actually tells us we should do about it.
So, let's just jump right in with a question that sounds, well, completely backwards. Can your data be too good? And if it is, are you allowed to just, pretend it's not there?
And believe it or not, this isn't some abstract puzzle. A real researcher actually ran into this exact problem and posted about it online. The answers he got back get to the absolute heart of what it means to do honest science.
All right, so let's break it down. What was the specific problem this researcher was dealing with?
So here's the scene. A computer scientist is testing a new algorithm. He runs it 10,000 times to see how long it takes. But a tiny handful of those results, like 5 of them, were just unbelievably fast. We're talking orders of magnitude faster. The problem was, when he tried to plot all 10,000 points on a graph, those 5 super fast points were so far away from everything else that they squished the other 9,995 points into this unreadable blob. So he asked, hey, can I just drop these 5 points to make my chart look cleaner?
And the answer he got back from fellow scientists? It was a big, fat, resounding no. And the reason why is what's so important here. It's all about the hidden story that those weird data points, those outliers, are trying to tell you. And here's why. This quote really gets to the heart of it. The goal of science isn't just to prove you're right, it's to uncover what's really going on. You can't just toss out data because it's confusing or makes your graph look weird. You have a duty to figure out why it's there in the first place.
This reminds me of that classic saying, real breakthroughs rarely come from an experiment that works exactly as planned. They almost always come from the unexpected result, the one that makes you step back and go, that's weird. That's where the new discoveries are hiding. So what could these crazy fast data points actually be? Well, they could be a bunch of things, right? Maybe it's just a bug in the code or a faulty sensor, but it could also be a hint that your entire theory is missing something crucial. And if you just quietly delete that data, you might be sending other scientists on a wild goose chase when they can't get the same clean results you did. Or, and this is the big one, you might literally be throwing away the most important finding of your entire career.
Okay, so you can't just hit delete. That's a huge no-no. So what do you do? How are you supposed to build an honest model when a few bizarre data points are yanking your results all over the place? Well, this is where some seriously clever statistics come into the picture.
The answer is, you have to build something smarter. You need to build what's called a robust model. Now, this sounds complicated, but the idea is actually super elegant. It's a concept called whole robustness, and it's basically a method where the model itself learns to tell the difference between good data and junk data. The more extreme an outlier gets, the less the model listens to it, until eventually its influence just fades away to nothing.
Okay, so how on earth does that work? Take a look at this chart. That dashed line, that's your standard bell curve. See how the ends, the tails, drop off really fast? Now look at the solid line. That's our robust model. In the middle, it's pretty much the same, but look at the tails. They're much thicker, or heavier. These are called super heavy tails, and they're the secret sauce. They create this kind of buffer zone that can handle extreme data points without the whole analysis falling apart.
This little table really breaks it down nicely. With a normal, everyday model, a single outlier has unlimited power. It can just drag the result wherever it wants. Other models, like the one in the middle, give you some protection, but a really strong outlier can still cause trouble. But the robust model on the bottom, it's completely different. The more extreme the outlier gets, the less influence it has, until it's basically ignored.
And the cool thing is, you only need 2 basic conditions to make this work. First, obviously, you have to use one of these special models with the super heavy tails. And second, and this makes perfect sense, you just need to have more good, trustworthy data points than you have outliers. In other words, the truth just has to outnumber the noise. All right, this is the really cool part. Let's actually watch this model in action and see the math do its thing.
So here's the setup. We've got 21 perfectly normal data points, all clustered together. Then we're going to add one single outlier and just drag it way out to the side, all the way from 0 to 100, just to see how our models react.
First, keep your eye on that dashed line. That's our regular, non-robust model. And watch what happens as that outlier gets pulled further and further away. The model just follows it blindly. That single bad data point is completely wrecking the result. Okay, now, look at the solid red line. That's our robust model. And at first, it does the exact same thing. It follows the outlier, Because, hey, maybe this is important new information. It's listening, it's trying to learn. But then, watch this. It hits a kind of tipping point, a threshold. The model's own math detects a major conflict here. It basically goes, wait a minute, this one point just doesn't fit with the other 21. It's like a little statistical alarm bell just went off inside the algorithm.
And this is the magic. Right after that threshold, the model just starts to tune it out. You can see the red line starts to curve back down, away from the outlier and back towards the real group of data. It has literally decided to stop listening to the nonsense.
And so as that outlier just flies off into the distance, look what happens. The robust model settles right back down, giving an answer that's based almost entirely on the 21 good data points it trusts. It found the truth, even with a major distraction.
So pulling it all together, what's the big lesson here? What does this all mean for the big picture?
Well, the takeaway is that science isn't about finding the prettiest graph or telling the cleanest story. It's about being honest about reality, warts and all. And these robust models, they give us a mathematical, principled way to do that. They let us handle the weird stuff without either letting it ruin our results or having to just unscientifically pretend it doesn't exist.
And really, that leaves us with one last thing to chew on, doesn't it? Whether we're staring at a spreadsheet or just looking at our own lives, what important hidden truths might be lurking inside the things we're most tempted to ignore just because they're a little bit messy?